Super.
Research scientist at Space Flight Center. Next slide. My research and application work involves exploitation of data from NASA's Earth observing systems to understand the climate drivers of ecologically coupled vector-borne and zoonotic diseases. Such data sets as shown on this slide include long-term measurements of sea surface temperature, rainfall, vegetation, and land surface temperature. The mix of these observations allows us to understand how variability in sea surface temperatures influences patterns of rainfall and temperature and other variables globally, and consequences on the land surface through patterns of floods and droughts, which in turn lead to disease outbreaks. Next slide. One aspect of climate variability that we pay special attention to is the El Niño Southern Oscillation. This is an internal mechanism of the climate variability which can be traced back to over 500 years. It is defined by the anomalous warming termed El Niño and cooling termed La Niña, ocean temperatures in the eastern equatorial Pacific, as shown in red and blue on the ENSO index in the graphic on the top left. These changes in ocean temperatures are coupled to atmospheric circulation. Now, due to the sheer size of the Pacific Ocean, these variations have downstream impacts on patterns of rainfall, temperature, and other variables across the world. The remote connections are termed as teleconnections and illustrate how Earth system components are connected. The two maps at the bottom illustrate the typical rainfall response patterns across the world during each of these events, either La Niñas or El Niños, with some regions receiving above normal rainfall and others experiencing drought patterns, with consequences to disease outbreak patterns globally. Next slide. A good illustration of these patterns is the recent 2015-2016 El Niño event. The two maps on the right show sea surface temperatures anomalies at the top and rainfall anomalies at the bottom during the peak period of this El Niño event between December 2015 and February 2016. Working with the interagency partners, including Defense Health Agency, USDS Center for Medical, Agricultural, and Veterinary Entomology, and non-governmental partners, including International Society for Infectious Diseases, ICID, and EcoHealth Alliance, we were able to gather in real time disease outbreaks that occurred during this El Niño period between May 2015 and April 2016. The map on the right shows the various disease manifestations around the world, including a huge cholera epidemic in Eastern Africa, dengue in Southeast Asia, dengue and chikungunya in Central and South America, plague and hantavirus outbreaks in Southwestern United States. What we learned from this process is that variations in patterns of rainfall, flood and drought, temperature and vegetation conditions favor the emergence and increase in populations of different disease vectors, including mosquitoes and rodents, therefore amplifying or triggering epidemics of human and animal diseases that can persist for months or years if not controlled. Next slide. The following animation illustrates how we can tie together these ENSO events, showing variations in sea surface temperature with patterns of disease outbreak globally for the period 2009 to 2018. On this animation, warmer than normal sea surface temperatures are shown in brown shades, and colder than normal temperatures are shown in shades of blue. You can notice the sharp elongated structure of El Niños and La Niñas in the eastern equatorial Pacific Ocean. The ENSO index shown at the bottom of the visualization enable us to track and identify El Niño and La Niña periods. Different colored dots on the land surface represent locations of disease outbreaks, with clusters showing possible epidemics of a given disease. Next slide. Now, digging deeper, we can look at what was happening in Southeast Asia during this 2015-2016 period. This animation shows the influence of patterns of rainfall variability that resulted in dengue outbreaks in Southeast Asia. Green shades show areas of above normal rainfall, brown shades show areas of below normal rainfall, and the purple pins show locations of dengue outbreaks. Warmer than normal temperatures during drought periods tends to increase the populations of Aedes mosquito species that transmit the dengue virus in densely populated urban environments. The plot at the bottom is an index of rainfall with the number of locations reporting dengue activity between January 2014 and December 2016. We can be able to track the emergence of the disease activity as the drought persisted over Southeast Asia, the peak conditions of the disease activity, and the recession in concert with the rainfall anomaly patterns against the background of this 2015-2016 El Nino event. Next slide. This following animation shows the sequence of monthly satellite vegetation, normalized different vegetation index for Africa and the Arabian Peninsula from 2015 to 2016. We use this index as a proxy to infer habitat conditions that are suitable for emergence of mosquito vectors of Rift Valley fever, a zoonotic disease of livestock and humans. Positive anomalies are shown in the gradients of green colors associated with periods of above normal rainfall, while shades of brown are associated with lower than normal rainfall and an indicator of drought periods. Brown pins on the map indicate locations where Rift Valley fever outbreaks were reported that occurred in association with greener than normal or above normal rainfall conditions. One important revelation from this work is a tendency for Rift Valley fever outbreaks to occur in Eastern Africa during El Nino events, for example, in 2006 and 2007, and over Southern Africa during La Nina events, for example, during the period 2009 to 2011. This is a clear illustration of how climate variability induced by El Nino teleconnections has an influence on disease outbreak patterns in different regions. The outbreak of Rift Valley fever in 2018 between March and June doesn't follow this particular historical pattern and indicates the increasing role of climate extremes in a changing climate can have on unusual disease outbreak patterns. Next slide. Now, equipped with this knowledge and research that we have done on various diseases, we are working with several partners to create a big data disease risk mapping and forecasting models, combining disease outbreak information from ProMed, Pan American Health Organization, and Defense Department, and also human population density and mosquito vector distributions that transmit the disease chikungunya. We combine this with dynamic satellite data inputs from NASA and NOAA to generate forecast. So slide 9, next slide, is a good example of this activity, showing the global chikungunya forecast system that is now providing forecasts of regions at risk to chikungunya activity up to 3 months in advance, with associated information on trends in outbreak patterns to enable PAHO and DoD and other public health agencies elsewhere to undertake prevention and control measures early enough to reduce the burden of chikungunya vector-borne disease. Next slide. All this information is combined together in an application that we are calling ChickRisk app. This is open and publicly available for use. This work is enabled through the support of NASA Applied Sciences Health and Air Quality Program, Defense Health Agency, Defense Threat Reduction Agency, NOAA's International Research and Application Program, and executed in collaboration with NOAA Climate Prediction Center, USDA Center for Medical, Agricultural and Veterinary Entomology, International Society for Infectious Diseases, promote global disease surveillance efforts, EcoHealth Alliance, and Pan American Health Organization. Thank you.